There we go. Don't know what the quality of video is going to be, but it shouldn't stop during the class. All right, we have a couple more people here. Any questions?
Yeah. On the lab.
Yes.
So what it has on the, I think it's the same page on results A, like what it says F theoretical and Y theoretical, like what is it asking for?
What is the what?
What is it like asking for?
Still, I missed the last.
What is it like? What do you want us to do, basically?
Right. So basically, it's in essence we're doing box on ramp, except we're ignoring friction, other than the analysis question. So if we did the force diagram of the box, we have weight acting down and normal force acting perpendicular to the ramp. So this arrow right here is supposed to be pointing straight down, and that one is supposed to be perpendicular to the ramp. Because acceleration is going to be in the direction of down the ramp, we would need to break weight up. And so we end up with W sine theta going down the ramp, normal force still perpendicular away from the ramp, and then towards the ramp is W cosine theta. This is a nice ideal situation right here. No friction whatsoever. And we assume that the slope of the ramp, some angle theta, the slope of the ramp is constant, which for the most part it is. Those tracks aren't warped too badly. But there are a couple places where you can put the cart on it, you can lay it down flat, put the cart on it, and it won't move. We put it into a different spot and it'll start to roll. So the tracks are not perfect. But in a nice ideal situation, this is the breakdown of the forces. So in order to keep it from rolling down the ramp, in other words, that force to keep it from rolling down the ramp would have to be equal to that. So this is the theoretical force down the ramp, or net force.
So which one, so would the sine one be Y and the cosine be, well, the F? Like I'm like there's certain like letters in each one. So with these two, which one would be the W sine theta and which one would be the W?
Why is the, all right, so if we plug into F equals MA, this is the net force acting on the box. Well, since it's going to accelerate down the ramp, that's the net force right there. These two will balance each other out. Generally, the wording is they cancel each other out, but they neutralize each other. So I have W sine theta is equal to mass times acceleration, and then Y minus W cosine theta, let's be formal about it, or at least more formal. I hat down the ramp, J hat away from the ramp. So Y minus W cosine theta is equal to 0. Doing substitutions and a little bit of manipulation here. This becomes mg sine theta is equal to mass times acceleration. And y equals mg cosine theta. This is, ideally, this is the net force acting on it. Because the net force is equal to mass times acceleration. That's that, depends on how you're going to count it. But that's the F theoretical. Theoretically, y is going to be mg cosine theta.
Okay.
curious what that's gonna look like on the video. Will we see any of your head at all?
Yeah, just a
You
little
will see
bit.
all of it. Wait, it's not barely.
You ducked, so it's possible you're completely out of frame.
You just sort of
Oh, you
peeked
saw,
into the
that's
lower-
right, you could see it.
Yeah.
Okay.
You just sort of peeked into the lower left corner, just a little bit.
Other questions? All right. Let's see if there's something I've missed. All right, so let me just work through one other type of problem that generally you start out with on these. It's gonna be an equilibrium problem. Right, and the eraser disappeared. And I feel like they replaced the board with the old one. So let's make that 50 degrees. And make that one 30 degrees. What is the tension in each room? Assume that the whole thing is just sitting there, that not only is it in equilibrium, it is in static equilibrium. So let's parse it apart. What does that mean? First off, what does equilibrium mean?
There's no, acceleration.
All right, that's a big one right there. What else does it mean? Or should I nitpick that?
No acceleration due to gravity?
Oh, no, that's still there. We assume that there's a planet below.
Sorry, never mind. I was trying to correct the acceleration versus acceleration due to gravity, but I don't know if that's what you're getting at.
Yeah, no, that's not it. All right, so I've taken us this far, so let's go ahead and nitpick. The spirit of what you're saying, absolutely right. However, let's think about slopes of lines. What's the slope of that line?
0.
What's the slope of that line?
Doesn't really have one.
Okay, so when you say there's no acceleration, do you mean acceleration is 0 or that it doesn't exist?
What I meant was that it doesn't exist. It's 0.
Yes, there we go. Yeah, acceleration is 0. And so when people say there's no acceleration, I know what you mean, and I probably have done this, and there's probably lots of video evidence of it as well. However, properly, acceleration equals 0. All right, so the equilibrium part, we have acceleration is equal to 0. What are the other two automatics for equilibrium besides acceleration being 0? If acceleration is zero, what else has to be true?
Velocity is constant.
There we go, that's another one. So change in velocity is zero. And yes, along with change in velocity being zero means the speed doesn't change and the direction doesn't change.
Is it that the forces should cancel out? It's static equilibrium?
Yeah. Equilibrium.
Okay.
Static, we haven't done the static part yet. So the net force is zero. It's the differentiative from O. Coordination issues today, apparently. All right, so now the static part. What does static mean?
That speed and velocity wouldn't matter. Speed and velocity won't matter.
Oh, depends on what you mean by that. I would say it still matters. But not generally the wording I was expecting. Do you want to expand on that, or do you want to let someone else pick up from there?
I'll let another person.
All right. I'm sure they appreciate your wanting to share.
Is it that the box or object in question is not moving?
Right. Static means the speed is zero.
Okay.
On the test, that the object was just in equilibrium, and there were a number of people, and I asked the question for several different groups, and I can't remember what this group said versus another group, but there were a number of people who felt that equilibrium meant that object is not moving. That is not true. Static equilibrium means it's not moving. If it is moving, what kind of equilibrium is it called?
A dynamic.
Yes. Now, it could be in dynamic equilibrium. In other words, this could be part in a spaceship that is traveling at a constant velocity through space, and we don't have to worry about, and it's not going to change our final results here. As I said that, I realized that then acceleration due to gravity would go to close to zero, and yeah, that's a rabbit hole I didn't want to go down. All right, so where we are, static equilibrium, it's not moving. It's basically, I have ropes tied to a ceiling and a mass hanging down. Force diagram. On a problem like this, how many objects are there? I mean, because how many pieces should I break it up into?
5?
What are the 5?
The 3 ropes, the ceiling, and then the box.
Oh. Then you've lost one. I was gonna be really impressed if you got the 5 I was thinking of.
The intersection between the 3 rows?
Yeah. So when you're given a problem like this, it's usually not stated. Sometimes they'll throw that they're attached to a ring or something like that, like in the force table lab, but it's not necessarily stated. And you do have the connection point that you have to worry about. I'm gonna rewrite this over here, so I'm gonna erase it. This is not meaning that there's a mistake there, it's just that I wanna give myself more room and I wouldn't not have to crouch down so much. And the connection point. Sure, I'm gonna give myself a little bit more room there. All right, so forces. We're still doing FCOM.
Well, we do in fact have acceleration due to gravity.
Therefore, what is the force involved?
It's moving down on the box.
And the force is?
Weight.
Yes. Yes. Do not put acceleration due to gravity in the force diagram unless you need to make some note to yourself. You would put it off to the side. Don't add it as part of the diagram itself.
Are we not including the ground? so that we can have the opposite force.
There we go. Now, the reason why I've gotten a little sloppy there is that ultimately, I care about this, the connection point and the box. Those are the two that are gonna have the primary importance in this. And so, but, we're still in the beginning stages, so probably should have it around there too. All right, so, any other gravitational forces?
Do the ropes have mass?
Let's assume ideal. So we'll go ahead and make that official. Now, this is gonna get into a little bit of, when you get the complex force diagram problem versus getting, trying to actually solve a problem. The ceiling has a weight. If this were the complex force diagram problem, then yes, I would expect you to put in the weight of the ceiling. It doesn't matter for this particular problem, we're gonna narrow it down much more, but just for the sake of fun, the subscript there, see. And I'm gonna leave a subscript off of that one. I'd put a B there if I was going to, if I were going to. The big thing is that those are not the same.
There shouldn't be any normal force.
Correct. Normal force done, gravitational force done.
Wait, but wouldn't there be a normal force with the box and the rope? Cause they're like, there's contact, right?
There is contact, but how is it contacted? How is the rope attached to the box?
The rope is massless?
It is massless, but it's gotta be, if you're saying there's a normal force there, you're indicating you know how the rope is attached to the box.
Okay.
So we don't know, so what are we gonna call that force? I think somebody just said it.
Tension.
Yes,
Oh, okay.
yeah, that gets lumped into tension. So I have tension there. Which way is the tension acting on the box?
Up.
Where's the other part of that pair?
Pointing down from the rope above it.
All right, so I'm gonna have three different ropes here, so I will have to have subscripts next to the tension. When we did all the problems we've done before that, we had one rope, so we didn't have to have subscripts if the rope was ideal. One of these markers is just gonna absolutely thrill me. So, why don't I label this rope 1, 2, and 3. All right, what else?
There's the tension between the bottom rope and the point.
Okay.
And then the same is true for the other two ropes on the point object.
All right, so this was FT, so that's 2. I'll go ahead and do this part. No other, there's things taken care of. Actually, there is another. Again, it's not relevant to this particular problem, but there's something else that has to be in here that does not look. I didn't actually state it in the problem. But what's missing?
And that's holding the ceiling up.
Yes, there's gotta be something holding it up. F sub ceiling. in some particular direction. Potentially, there's also a sideways component. We don't know yet what the tensions are. What about friction?
No?
Does no with a question mark?
Yeah, I believe it's no.
Oh, a little bit
I'll
more
go
confident
ahead,
on
I'll
that
go
one.
ahead and say no, let's get rid of the question mark.
Right. Friction requires a desire for two objects to slide against each other, but there's, the intent was that the rope is attached at some point at the ceiling, and it's not on some glider that can move. Like track lighting? Yeah, because track lighting's got a groove where they can slide. And what I care about is this and this. Now, some of you might look at this and go, couldn't we have done a shortcut there? And yes, there's some shortcuts that could be taken. If you see the shortcuts and know how to use them, go for it. All right, so what we have here is taking the parts that I care about. I have tension 3 at an angle of 50 degrees. I have tension 2 at an angle of 30 degrees. And then acting straight down, I have tension 1. And then I have another place where I've got tension 1 up. And I've got weight of box acting down. And we're going through our process here. There's the force diagram, then the remaining parts. What is the direction of acceleration?
Down, yes.
Why?
It's the easiest one to line up, I guess. So we already know the angles of the other ones, so it'll be easier to just put it in that direction.
But if acceleration is equal to 0 meters per second, does it have a direction?
No.
'Cause it's not moving.
Well, we just gotta pick one, right?
If the last bit about whether it's moving or not is irrelevant.
0.
Whether it's moving or not can affect friction if friction is involved, because has it overcome the static friction, or is it automatically in the dynamic? But this is not gonna move because it's static equilibrium. But because acceleration is 0, there's no specific direction. Direction can be anything you want it to be. So when you get over here to try to figure out you want for your coordinate system, whatever is gonna make the math the simplest.
Seems like no matter which way we put it, we'll have to break 2 of those vectors up into component parts.
We will, agreed. So, if you pick that as your system, so that this is in the direction of tension 3, what is the angle that this makes with, I guess, the j-axis, or I'll make that I-hat and j-hat. What angle is that making?
Is it 100?
It is 100 degrees, and this one? All right, so this is completely legitimate to do it this way. As a matter of fact, there's a test problem that you'll probably get where I give you the force diagram and ask you to come up with the equations of motion. So basically, I give you this, I tell you the acceleration, and then you have to come up with this. So you have to determine what the coordinate axes you're going to use is. All right. And so this is perfectly legitimate for an object in equilibrium, absolutely no problem. The trouble is, you have to do the additional math in order to figure out that direction, which wasn't too hard. There's a 100-degree angle between there, and then this one right here. If you had gone the other route and chosen a marker that's on its way out. It shows that that is your coordinate system. Well, you don't have to break that one up, you do have to break this one up. Again, there's a 100-degree angle between these two, and you still have to figure out what that direction is. So, going along with Ian's suggestion, I guess you chose down, and then that'll force the other one to be left or right. The advantage of this one is, again, you only have to break two up, but at least you're given those angles. I could have made it more complicated on that decision process if I had given you, I guess, this angle right here instead. Then you have to do some little bit of extra math there. But this is the recommendation that I would take, or up or down, whichever one you want to make positive. I think ultimately it's just gonna be simpler math. All right. We gotta break two things up. Well, tension 2 and tension 3. So tension 2. So the one that's horizontal here, is that gonna be a cosine or sine?
Cosine?
With a question mark?
Yes,
I also think it's cosine.
because I think it would be the adjacent side to the angle, considering 30 degrees is theta.
Okay. So this is gonna be ft2 cosine of 30 degrees. ft2 sine of 30 degrees. And I'm gonna write that over here. And the reasoning was absolutely right, it is adjacent for that angle. So which is the horizontal here? Or what is this? Breaking ft3 up.
ft3 cosine 50 degrees.
And so this will be the other one. So we've basically taken the three forces acting on the connection point, split up the two vectors that we had to break up, and so this right here is a substitution for this.
Are we still calling this vector that's pointing down ft1?
Yes, thank you. Equations of motion.
ft3 cosine of 50 minus ft2 cosine of 30 degrees?
Oh,
For
sorry,
positive
do
I
that.
hat minus,
Yep, sorry,
That's
my
fine.
mind was on a different arrow.
it seemed just as likely that I was totally off base.
For some reason, the word co got blocked from my head,
Hmm.
and so it became ft3 sine 50. Equals,
Mass times acceleration. But there's no acceleration, so it's 0.
sure,
Okay. Sorry, acceleration is equal to 0 in the I hat direction. So it's equal to 0.
and we start to speak like that on a regular basis, your family just loves it. All right. Another equation of motion.
It would be ft1 minus ft2 sine of 30 degrees minus ft3 sine of 50 degrees. Is equal to 5 times 9.8. I was trying to do mass times acceleration.
Yeah,
We'll go MA, oh, we're not plugging numbers in.
It's just
Yeah,
zero, isn't it?
Would it still be zero?
Oh,
F equals MA, that A is the acceleration of the object, not
right.
If-
regardless of whether there's a gravitational field or not.
It would be little g if it was.
Right.
Acceleration due to gravity.
Absolutely.
Okay.
And then the third equation of motion.
Is it something that indicates that there's no friction, one of those like
No,
U
no.
equals zero?
All right. We have two directions here, we have two equations of motion. Don't forget, we do have a second object.
Oh,
That's the weight minus the FT1 equals, zero.
I hope so. If it doesn't equal zero, then somehow we have these three ropes connected at a central point, not accelerating, and this box is accelerating. I guess that rope would have to be stretching. In which case it's no longer ideal. All right, so we have three equations of motion. Yes?
Yeah, for the third one, wouldn't it be, like, wouldn't, weight be negative? Since
Why?
It's going down,
And
and FT1 being positive? Or does it not matter?
you could have done that. You don't have to have the same convention for both objects. Especially since there's no acceleration, there's even less of a desire to have that sometimes. But I was sticking with the same convention that Ian had set up. So if you wanna make up positive for the box, that's perfectly fine.
But I would have to flip that, the I hat and J hat that you made?
Not, I mean, you could still keep this for this object, and then for this one down here, just make up positive for this object. There's nothing wrong with doing that.
Okay.
Generally, you want to have, both of them have a positive direction that's in the direction of acceleration, if their accelerations are the same. But since the acceleration is equal to zero, I almost said it wrong. Since the acceleration is equal to zero, do whatever you need to.
Okay.
would it not goof up your math if you were to change the coordinate axes? I mean, it would reverse,
That's what would happen. If you suddenly make a positive,
right?
which means that I would add W to both sides, whereas before, I would add tension to both sides, and either way, I've got weight is equal to tension.
I see, okay.
All right, so physics has gotten us this far, boom. Substitution, a little bit more physics, and then we get to the math part piece.